Hi, my name is Brian Caffo, and this is the lecture on p-values in our Statistical Inference Coursera class. This is part of our data science series and is taught by my collaborators Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Bloomberg School of Public Health at Johns Hopkins. So p-values are the single most common measure of statistical significance. So their ubiquity, along with the concern over their interpretation, makes them controversial among statisticians. People love to fight over p-values, love. And here's some instances where people criticize p-values quite forcefully and with a fair amount of intellectual merit. My favorite is "The Earth is round, p less than 0.05." I just like the title. But I also really like Richard Royal and Steve Goodman were both former faculty members at Hopkins, and they kind of highly influenced my thinking about p-values. There's this nice reference by the blog Simply Statistics on p-values that you can read. This well-known statistician named Larry Wasserman wrote a wonderful blog post about p-values and correctly interpreting them, and the same could be said for this person. The blog Error Statistics is actually written from a philosopher who spends a lot of time thinking about the philosophy of empiricism and the philosophy of statistics, and her name is Mayo, and she's written a nice post there about misinterpretation of p-values. So, any rate, you can read over those. All of these references, I think, are quite accessible and are good introductions to maybe why people have such passionate feelings about p-values. So we'll just in this lecture tell you what they are, and then you can read more about controversies and things like that, because you need to know what they are before you can dive into the controversies. So here's the idea behind a p-value. Suppose nothing is going on. How unusual is it to see the estimate we got? So we're going to define a hypothetical distribution of our statistic when nothing is going on, i.e. the null hypothesis, and we're going to calculate the statistic with the data that we have. That's our test statistic. And we're going to compare what we calculated, our observed test statistic, to the hypothetical distribution and see if it was outlandish, right? So the idea being, if you get a low probability for this, right? If you get a low probability of getting something as extreme or more extreme in favor of the alternative where the probability calculation was under the null, that means one of two things has happened. Either something very odd happened, either the null is true and something very odd happened, or the null is not true, okay? And so people tend to reject the null hypothesis, or the idea is you reject the null hypothesis when the p-value is small. So here's the definition of a p-value. The p-value is the probability under the null hypothesis of obtaining evidence as or more extreme than will be observed by chance alone. So, if here's our distribution of our normal test statistic under the null hypothesis, z statistic under the null hypothesis, here's our test statistic, z observed. Our p-value is the probability of getting evidence as or more extreme. So it would be, if we're testing h naught mu equal to mu naught versus ha mu bigger than mu naught, it would be this probability up here, right? So if your p-value is small, then either h naught is true and we've observed something that's odd, right? It would be rare, for example, to observe a test statistic way out here if the null was true, because the probability of observing something that extreme is very small. Or the other alternative is that h naught is false. So that's why it's commonly stated that small p-values are evidence in favor of the alternative. So in our example, our test statistic was our t statistic was 0.8, and it was 15 degrees of freedom. what's the probability of getting a t-statistic as large as 0.8? So what we want is, here's our t-distribution, here's 0, here's our test statistic, which works out to be 0.8, and the probability of getting a t-statistic that large, right, that works out, we calculated over here, to be about 22%. But usually, by the way, we consider two-sided hypothesis tests. So we consider the probability of either too large or too small, as in lower than negative 0.8. So the p-value would be 44% if we were considering a two-sided test. That's why for two-sided tests you double the p-value. We'll talk more about that. So therefore, the probability of receiving evidence as or more extreme than actually obtained under H0, the probability of seeing evidence as or more extreme than actually obtained, comma, under H0 is 22%. So there's a related idea, in fact, numerically equivalent idea of the so-called attained significance level. Our test statistic was 2 for H0 mu equal to 30 versus HA mu different from 30 when we said that n was 100. Okay? So here's our normalized test statistic distribution under the null, and our test statistic works out to be 2. And we said for a one-sided test that if we set alpha to be if we set alpha to be 5%, right? Then we got 1.645 there. We set that to be 5%. Our 2 was bigger than it, and we would reject the null hypothesis. What if it was 0.1%, right? That would be way out here, so that there was 0.1%, right? Then we would, if we set alpha to that level, we would fail to reject. So look at what would be the alpha level for which that you exactly achieve this balance, where if you pick, if you were to have picked an alpha level larger than it, if you were to pick an alpha level larger than it, you would reject, and smaller than it, you would fail to reject. Well, I think you can see, if we picked up here, we're going to reject. If we picked down here, so that our alpha level is this guy, we would I'm sorry, if we picked up here, we would fail to reject, and we picked up here, we would reject. So I think you can see, if you were to move it so that the line exactly overlapped with your test statistic, you would be exactly at that point, and then that alpha level would be the alpha level for which you fail to reject if the alpha level were smaller than it, and you reject if the alpha level were bigger than that. And that guy is called the attained significance level, kind of for obvious reasons. It's sort of saying, what's the smallest significance level I could choose and still reject? So you can see this is equivalent to the p-value, right? You can see that by moving these lines around until we get to that perfect alpha, that probability of being larger than our test statistic, well, that's also just the p-value. So it's philosophically different, but it's the same quantity. It's the same number. So anyway, there's a difference between there's a interpretation difference between the attained significance level and the p-value, but there's not a practical difference because they're the same number. One reason I like p-values is if someone gives you a p-value, then the reader or interpreter of your test can perform the hypothesis test at whatever alpha they like. They reject if the p-value is smaller than alpha, and they fail to reject if the p-value is larger than alpha. Okay, so that's one reason why I like p-values, is because then the person can calibrate the test however they'd like. If you just tell them I rejected or I didn't reject, you haven't given them the same amount of information. For two-sided hypothesis tests, you double the smaller of the two one-sided p-values, right? So, if your z distribution looks like this, and you got a test statistic right there, here's the here's the p-value for that direction hypothesis test, here's the p-value for that direction hypothesis test. You take that guy and double it, and that's your p-value. Okay, let's calculate a p-value not just for a normal example, which we've already done. Let's calculate a p-value for this binomial example. Your friend has 8 children, 7 of which are girls, none are twins. If each gender has an independent 50% probability for each birth, what's the probability of getting 7 or more girls out of 8 births? That's a p-value. The probability of getting, if we're testing the hypothesis that h naught p equal to 0.5 versus ha p greater than 0.5, more evidence would be more of the children being girls, and so the probability of getting our observed amount was 7. The probability of getting 7 or more, right, is probability of 7, and then plus the probability of 8 works out to be about 4%. Okay. And then you could just do this with p-binomial. Remember, you have to do 6, because if you do lower tail equals false, it does strictly greater than, so it starts counting at 7 when you put in 6. But if we were to put in 7, it would start counting at 8. Let's do a Poisson example. Suppose that a hospital has an infection rate of 10 infections per 100 person days of risk, which is a rate of 10 over 100, or 0.1, during the last monitoring period. Assume that an infection rate of 5% is an important benchmark. Given the model, could the observed rate, I shouldn't say 5%, the given infection rate of 0.05 per day at risk is an important benchmark. So given the model, could the observed rate being larger than 0.05 be attributed to chance? That's what we want. That's what we want to test. So we want to test whether h naught lambda equal 0.05. So if lambda was 0.05, then lambda naught times 100 is 5, right? So if the rate is 0.05 per day, then the rate when monitored for 100 days should be 5. So we want to test HA lambda greater than 0.05, because we're interested in whether our infection rate is higher than this benchmark. So we would do our Poisson probability of getting 9 or more than 9 with a rate of 5. We do this again more than 9 because it calculates the probability with strictly greater than. So this will count 10, 11, 12, so on. Okay? And that gives us a probability of 3%. So we would, if it was a one-sided test, we would reject. If it was a two-sided test, you double it, right? You double the smaller of the two one-sided hypothesis tests. And so that gives you 3 different settings in which you can calculate p-values. We went over a normal p-value, which is pretty easy. We went over a binomial p-value, and then we went over a Poisson p-value. And in each case, we did the same thing. We specified our hypotheses. We calculated the probability of getting a test statistic as or more extreme than was actually observed, where this probability was calculated under the null hypothesis. That quantity is a p-value. You're going to reject if your p-value is smaller than your alpha level, and you're going to fail to reject if your p-value is larger than your alpha level. And then now that you know what a p-value is, you can go and read some of those references and see all the fighting about it.